1, 2, 3, okay, so like 5 of you. So, and I'm not even just talking little hardware like this. This is a neat little device. It's called the Node MCU. Strangely enough, it runs MicroPython. But I'm talking big servers as well. And one of the neat things about this is software, we've gotten really, really good at making software. And, you know, you all are software developers. We're at the point where you should also be developing your own hardware. Who thinks developing your own hardware is hard? You're all correct, but it's easier than you think. So let's take a moment here. Oh, good, you guys got it. Let's take a moment here. How many people work in the embedded space at all? How many of you have even tried an embedded CPU? Great. This is good. You guys are going to all learn something really, really interesting, which is when you do embedded development, which Python has now, you know, dipped its big toe into the embedded space. The classical way that you do this is you start from nothing. Absolutely nothing. Just like this slide. And the first thing you've got to do is go and find all of your pieces and start like literally building everything from the ground up. So you start building stone tools. And by stone tools, I mean you go and you find the correct compiler for your platform, the correct C library, all the rest of the libraries, maybe a driver, a board file, a goat, because at some point you're going to have to perform a dark ritual on a black square in a server room. And you just kind of, you know, keep grabbing these pieces, putting them together, and maybe, if you're really, really lucky, you can get to the point where it's all installed, or at least you think it's all installed. And you end up with something that roughly looks like this. And I really wish I was joking, but most embedded development really does look like this, at least in its current form. And you think this is great, and it's wonderful, and you're ready to start writing Hello World because everybody starts with Hello World. I mean, who has not started your programming career with Hello World? Seriously. Did you blink an LED instead? Because if you blink an LED, that's Hello World. What? No, you don't count. You're too old. And you're an economist. He's talking later, so he can yell at me later. Okay, so you write Hello World and you try and compile it. And what's the first thing that happens? It works, right? Right? No, damn it. It doesn't work. It never works. It never bloody works. And you know why? Because the tooling's too hard. Embedded development is fundamentally built on this crazy deck of cards that one guy in his basement that works for some big company got working one night while he was on a bender and then could never get it to work again. And he's like, I'm just going to ship what I got and hope nobody notices and hope everybody can just copy it. So you sit down, you figure out what you did wrong, and you find the missing symlink that wasn't included in the tar file or the zip file because, no, actually it's a zip file on a Linux system, so the symlink doesn't actually work, and there's no like install script, and so you fix that. What? Somebody's making, well, anyway. So you get it all, so you finally get it, what you think all ready to go, and you type, you know, make to make your Hello World application again. And you're ready to go, and the build tool fails. And it falls over, and it crashes, and you're like, really? Really? Now I have to explain this to my boss, that it's not working, and I don't understand. And you're sitting there literally panicking. Because, like, tomorrow you've got to show the boss that the sensor works, and maybe, you know, maybe if I just bash my head on the table long enough, I will put together a string of characters that makes no bloody sense, adds +1, maybe 2. Or in Perl, you just, you know, it's line noise anyway. And it'll work. And you bang around on this for a while, and you hit make, and it works. And you think that you are on top of the world. It worked. It compiled. You're done, right? Right? Who's done embedded development? Are you done? Yeah, that's sadly the correct answer. Because a lot of embedded development boards, and on a side note, we are living in a golden age of embedded development, and and I don't want to use this magical dirty word called IoT, because good Lord, if you're not scared of IoT, you should be. I mean, it is the future. It's all going to happen. We're going to make a ton of money off of it, but I mean, who would have thought my video camera would be participating in a spam attack against, I don't know, Zimbabwe. No offense, Zimbabwe. But we live in a golden age where everybody's starting to actually, take embedded development and embedded devices and make them really, really easy and really, really nice to use. It's shocking. I mean, we have USB ports, and we have, simple GPIO pins, and we don't have all of these crazy things that we used to have many, many years ago. Back, when dinosaurs roamed the earth, and, yeah. But anyway, so I digress. We're at the point where we have a Hello World application, but we don't actually have any hardware we haven't put this on any hardware yet, so we don't know if it actually works. We're pretty sure it works. I mean, it compiled. Why wouldn't it work? So, we go digging around in the drawers. God, I gotta fix this picture at some point. We go digging around in the drawers because invariably we've got the wrong USB cable, or the hardware manufacturer decided to use some magical connector. I mean, you've all seen the power connector on Sony cameras. It's like this weird sideways U-shape that I've never seen any other power connector in the face of the universe ever use. And so you got to go find that thing. And at some point you find your parallel port, and you plug that into your laptop, and then you realize that you need to get it to a serial port, so you get it to a serial port. And then you realize you need to get it to a PS2 port, which, why in the heck do I program my embedded device with a PS2 port? I have no idea. I mean, it's just going to type keyboard commands for me, right? And then you realize, oh, wait a minute, I need USB. So you find a USB adapter, you plug it all together, you plug it in, and you go, great, let's try and run this Flash program. Well, first off, nothing ever is simple in the embedded world. At least mostly never simple, because you have to find the Flash program, because every board flashes its memory differently. I mean, it doesn't matter whether you could have 12 different ARM boards, all running the same CPU even, and they use 12 or 13 different ways to actually flash all of the boards. Okay, so you've got all the hardware set up. You really, 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 really want to run Hello World finally. So you get it plugged in. You try and flash it. And of course, you've done something else wrong, which is mostly you've just burned out one of your cables. Or you've plugged something in backwards because nothing's ever documented, which for those of you who will at some point go on and do hardware development of any sort, please put more documentation on your board about what everything is than you would ever put into a computer program. Because it's really, really easy to go, oh, there's a huge pile of these, pins. And one of these is ground, and one of these is 12 volt, and one of these is the thing I actually care about. Noting that the device in question can only handle 3 volt. And the magic smoke's out. Okay, I'm curious. Those of you who have done embedded development, and please, honest to goodness, be honest here. How many of you have let the magic smoke out? If I'm looking at these hands, everybody who claimed that they were an embedded developer before, I mean, seriously, look around. There are serious hands here. Every embedded developer has let the magic smoke out. Every one of them. In fact, I've got stories not doing embedded development, but doing big development. I've got PCBs on my wall at home that are seriously this big. That's a single computer. We accidentally had a manufacturing defect on one of those boards that caused an air gap on the power plane. It got really hot. You know what happens when things get really, really hot? They combust. And a 4-foot flame shot out the side of a PCB, is what read the toe tag on that dead board. It was only a $40,000 board. Wasn't mine. So yeah, I didn't have to explain that one to management. But needless to say, you're going to play, everything's going to be screwed up. Put more documentation on your hardware if you should ever get to that point. But what I'm really trying to describe here is that, okay, you've got everything kind of set up. You're trying to get it all to work. You finally try and get it to flash. You get it to flash. You get it, you get your program onto the board. You flip it over. And you actually try and run it. And then in classic fashion, everything on Linux breaks. And it doesn't work. And you're like, what have I done wrong? Why is my board on fire? Why is my board literally on fire? Because invariably, by trying to run Hello World, you've somehow overclocked the CPU on this little microcontroller and dumping 12 volt into a 3 volt line of some sort. And then everything breaks, and it catches on fire, and everyone's sad. But this is the way most embedded development works. And this is where you should all be really, really unbelievably happily glad. This is not how you develop MicroPython. MicroPython is much simpler. So I've obviously rewound here a little bit. And we're back to, I would like to write Hello World. So instead of, starting to try and compile anything, you go to MicroPython, I think it's .org or .com or whatever, you Google it, and you download the MicroPython version for your board. Most of the rest of this talk, I'm going to be specifically talking about the ESP8266, which, if you're unfamiliar with it, is a very nice little chip, and it's cheap. And it has Wi-Fi, and it's going to be the doom of all of us because of IoT. So you go and you download that, and it has these nice little instructions on how you flash it, and you spend 4 or 5 times desperately trying to figure out which command line option you've done wrong, which literally this is what happened to me, and you finally get it flashed. And you reset the board, and you're greeted with this wonderful REPL prompt. We're all familiar with REPL, right? Well, at least not me. I'm a Perl guy. And you're like, huh. Well, I can just start typing random stuff. So, you start typing, import machine, import time, you set up a GPIO pin. You flip it low, you flip it high, you see which way it actually flips, because invariably somebody on the hardware side has wired the LED backwards. So that when it's low, it's actually on, and when it's high, it's actually off. In fact, this is what I did on my own board, which I'll come back to. And you write this quick little for loop, and you literally get the embedded development world version of Hello World, a blinking LED that is no longer blinking because my video loop doesn't loop. Again, everything on Linux is broken. And I've been doing presentations for years and always doing it on Linux, and every time it's always broken. So, those of you, there was a question asked earlier is, how many people think that, Linux is simple? I've been doing Linux for way more years than many of you, and no, it's never simple. But I can't actually say I dislike it, so I'm just broken. So, it works, it's wonderful, it's great. And this is, for those of you who have not done any embedded development or have not looked at really like low-level playing with hardware, this is astonishing. This is beyond amazing. This is, I have pulled a random board out of a box, plugged it in, and I have a blinking LED in less than 5 minutes. I don't have to know any new programming languages, and it just works. This is amazing. So my hat really does go off to the MicroPython guys. They're doing an astonishing job. But this is all software. I'm not here to talk about software, although it really is amazing and it's awesome, and I want everybody to know exactly how awesome MicroPython is. I mean, if you can write Django, has Django been ported to MicroPython yet? Because honestly, it should be. It'd be awesome. Probably be too big, and you'd have to like attach an actual hard drive to your little embedded board that just reads sensor data. But you know what? Some of us, I'd be okay with that. But seriously, let's talk about hardware. Hardware is something, as software developers, we have a real problem with trying to grapple with. We understand hardware from a really abstract perspective, which is, that wonderful little terminal or your IDE in front of you. Or frankly, some of you may not even give a fig about what hardware you're running on. You may be so off, so high in the stack that you're a web application. You've got Django behind you. You don't care that there's spinning Rust on a hard drive or an SSD actually providing you the bits that are coming off of your laptop or your server's hard drive. You just want things to work. You just care about the software. But what's interesting here is that if you actually understand what the hardware is doing, you're actually a better programmer. And this is why I'm even here talking to you about hardware at all, is because I've known people who have gone through graduate level courses in computer science. They are absolutely brilliant, and they're scared to open up their computer. For fear of literally just taking the case off, they will let the magic smoke out. And if you drop a screwdriver or a screw or something like that on that 12-volt rail, short it to ground or something, you might. But you shouldn't be scared of this because the chances of you actually breaking anything are relatively low. Disclaimer, I will not be held liable for you letting the magic smoke out of anything you will do based on this talk. Mostly because I let all the magic smoke out of my own things and I have to fix them. But hardware gives you the ability to be a lot more creative in what you can do, particularly if you're doing your own. You're so used to, most software developers are so used to, going and finding the board that is closest to what they want, but it's not quite right, and it'd be better if it did this other thing, but I can't find one to buy. And the real answer is that if you're down in this embedded space, stuff's gotten so cheap and so easy to use, and stuff is so readily available for you to pick up that you should seriously, you might do some prototyping on that board that's close, but as soon as you've proven that everything's going to work, go and do your own board. And I'm not even joking about this, because it's so simple. I mean, I'm not sure that there's a whole lot of electrical engineers in this room, but this is the simplest circuit diagram I could draw for anybody. It's an LED. It's literally a battery, a resistor, and an LED. And if you, is there anybody who is confused by this circuit or by this schematic drawing? Because I'll go back through it again. I mean, it's a battery, it's a resistor, and it's an LED. You plug the battery in, and the LED lights up. When the battery runs out, the LED turns off. Yeah, that's easy. And this is seriously as easy as a lot of this stuff gets from the schematic perspective. And who in this room could probably replicate that, particularly if I gave you this picture?
I bet I could get the LED in backwards.
You would get the LED in backwards. Yeah, if your LED doesn't work and you're making your own board, turn it around. Because that'll probably fix it. But this is that's actually the schematic that was the schematic drawing for this particular PCB, which I just for kicks and giggles, made up at one point. We were going to use it as a party favor, and we were going to let people solder together their own little, crest for this party we were doing. And fortunately, there was a typhoon over here, and it showed up a day late for a one-day event. And but yeah, I mean, this is something that everybody can do. Seriously, if you can, draw the schematic drawing I just showed you, which is a battery, a resistor. Number one is reset wire. So everywhere that I have defined a wire that says, or a netlist item called reset, it connects to that. That's it. And if you go through this a little bit, there's some extra detail on how things got defined. Anything look super complicated on that, other than the fact that there's another resistor? Anybody think that's complicated? No, and I'm being serious here. If this looks complicated, stop me, and I will try and explain this better. Okay. But there's a lot of people who will come up and ask, well, how do I figure out how to put this all together? I'm not an electrical engineer. I have no clue how to use integrated circuit here. Well, there's two really, really exciting pieces of news for you. The first is there's this entire open source hardware movement. So if you're familiar with the way open source software works today, we're about 20 years into the life cycle of open source software. Open source hardware is just starting. So there's this whole new Wild West of experience Let me tell you, it's a disaster. Licensing is hard, the laws don't quite all match up the way we would like them to, and just everything's new and weird, and so everybody's trying to figure out how this all works. So if you're interested in getting in on the ground floor, open source hardware is great. You all seem to understand open source software. You run Python, right? So, well, here's the hardware equivalent. So that's the exciting thing, one, is that you can go and find all of these examples of things that other people have already done, which means you can literally copy and paste what someone else has done and just change it a little bit. Or, the dirty secret number 2, everybody who creates integrated circuits, Texas Instruments, Broadcom, Intel, they actually give you exactly how to put it together already. Now, you're going to ask me how. On the left, this is straight out of the data sheet for the MCP 73831, which is, and I'm going to completely forget, it's the LiPo charger on the board I was building. That is exactly what they tell you that your circuit should look like. So I copied it. And it's not like, you can just drag and drop, copy, paste like you would expect from Stack Overflow, which for the record, if you ever just copy and paste anything out of Stack Overflow, you should feel bad because you're a bad person. Because, good Lord, Stack Overflow is full of bad code. I mean, it's great for, double checking how you think you should do it or how you think you should not do it, which is more the latter than the former. But you can, in whatever CAD software you prefer, you can just copy and paste, or logically copy and paste exactly what the manufacturer gives you. And then you build up all of these pieces, and it's more or less a Lego brick at that point. As you can see, I've got a voltage bus coming in and a battery output going out. I could hook that up to any compatible battery or any compatible incoming bus, and it will just work. And once I've done this once, and I've vetted that it works, and I didn't screw anything up, and I didn't put the LED in backwards, or all those kinds of things, you've got this for every design that you do afterwards. And this is exactly why, the manufacturers want to make this easy for you because they want to sell you more chips. The open source hardware movement wants to show you how to put these together in new and novel ways, or at least give you a reference implementation so that you can do your own things. And it makes it really, really easy. So those of us in the software world, the barrier to entry, everybody thinks it's way up here. The real answer is it's down here. You don't need to know quite as much as about the electrical engineering side, because there are smart people already figuring that out for you. You just have to figure out what you want to do. So once you've gone through and you've created your giant schematic that looks roughly like that, you end up with a very exciting mess that looks roughly like that. This is actually what my board started as. When you've got your schematic, you can actually create all of the pieces that you're now going to do layout on. And you get all these nice little wires that you get to route. And there's something that software people will always run into when they start doing hardware. There's this magical thing called an auto router in a lot of CAD software. Don't use it. It's bad and it will break things and you won't understand why. So if you ever see the words auto router, ignore that it exists. Unless you really, really, really know what you're doing. Which, if we're all software people, we have no clue what we're doing. I have no clue what I'm doing. I don't know why I'm up here. Kushal, why am I up here? Kushal's insane. He doesn't know what he's doing either. Although he's running a good conference, so, hats off to Kushal. And more or less, what you're looking at here is each of those yellow lines is a wire that needs to be routed, or, that needs to be moved around. Or if you think about this in a breadboard sense, that's more or less what you have to do. Take all of these pieces and move these wires around to make hardware. And this can be really time-consuming because you're basically playing a giant game of Untangle, which everybody's familiar with the game Untangle, where you get this, you've had to undo a bunch of cables, that are all in a rat's nest. Well, this is pretty much what you're doing. So at some point you get bored and you go and you build a robot instead. although this is an old robot. And then a few more hours later, you go back to playing your Untangle game, which this is the Untangle game if you're unfamiliar with it. You get this big giant pile of mess, and you're supposed to make it a nice pretty graph. And at some point, many, many, many hours over over a holiday weekend, oh god, that really is terrible. That's unfortunate. If you ever want to see this picture better, come find me. I will show it to you, because this is much prettier than, unfortunately, what that looks like there. But you end up dragging all of those wires around, and exactly like that breadboard scene, you get this nice, pretty thing. And now you're done, right? All the hardware is done. You're ready. You're done. You can go take a nap, right? Except that this is still all digital. So you're like, oh, right, I have to actually build this thing. Except that I've now done lots and lots of work. Well, the nice thing is once you've gotten to this point, you can send off your design files to someone to manufacture for you. It's really awesome. In low quantity, there's lots of places around that will, literally take your designs and build them for you and ship them back to you for a price. In low quantities, it's a little on the expensive side. When you're building 10,000 of them, have them do that, because soldering 10,000 LEDs backwards and then having to flip them, as Stephen apparently puts his LEDs on backwards, that will happen. But you send this off to a board house. And this is where all of the digital stuff that we're used to doing. In software, nothing ever becomes tangible. Nothing ever becomes real. In hardware, everything you do, you want everything you do to become real. And so you send it off to the board house, and these machines, these fantastic machines. If you've never gone and looked at how hardware is actually built, go and poke around on YouTube. There are some amazing videos of the machines that make PCBs and how all of that layering works. There are some amazing videos of pick-and-place machines doing pick-and-place, which, seriously, it's a ballet watching those pick-and-place machines work when they're done correctly. And so this wanders off, and it goes to China, and it does, and China does, and as far as I'm concerned, it's magical black box that I don't know what it does, la la la, and I go and I take a nap. Or, in this case, I play NetHack. Giant NetHack for 3 weeks, 4 weeks, 6 weeks, 6 weeks. Because, I have nothing better to do. And this is one of the downsides to hardware. Compile time for hardware. We're all used to, run. Ta-da! I get results. Hardware, it's run. Week 1, week 2, week 3, week 4, week 5. Why can't I parallelize this? Week 6. And you get your thing back. And invariably, when you do your first board, if it works, pat yourself on the back, because it almost never works. Pat yourself on the back if the second one works. And usually by about the third or fourth time, it actually does work. So you get this board back. And how many people have done bring up on a brand new board before? Anybody? A couple over there, a couple in the back. This is unnerving, because you have gotten a piece of hardware back, and you have no idea if it works. You don't know if the serial console is going to work. Everybody knows what a serial console is, right? If you don't know what a serial console is, come and ask me about serial consoles later, and I will tell you how amazing serial consoles are. They are literally like the best thing ever, particularly in hardware bring up. You don't know if the serial console is going to work. You don't know if the LEDs are going to work, because they might be on backwards because you screwed something up like Stephen always does. Sorry, Stephen. And so you plug it in for the first time, and you hope this does not happen. Because this is literally what letting the magic smoke out looks like. But if it doesn't explode like that, you get something interesting, which I'm going to be a magician. Hat. I'm going to pull a bunny out of my hat. I seriously thought of this joke like 3 minutes before my talk. And the bunny works. And this is, in fact, running MicroPython. And there was a gentleman last night who, he's the second person to ever play with this. Like, literally, this is, board number 1, although my 1 apparently has come off. He was playing around with it last night, and he got the LEDs working. And the fact that most of this board works on the first try without me ever doing a prototype, it's not too bad. And this is something any of you can do. I mean, you can go and find examples of how to build these things off of open source hardware. You can find exactly how to use all of the integrated circuits because the manufacturers want you to use them, so they make it as easy as possible. And you can build things. You can build physical things. And then because I was bored, I built a second bunny. And you'll notice that the bunnies are actually slightly different, although I don't have a battery in one of them. This one actually has the ESP8266 soldered down on it, and this one uses the Node MCU that I started this presentation out with. For all intents and purposes, these bunnies are identical from a software perspective, and yet the hardware is fundamentally different. And this is why open source hardware or building your own hardware matters, because you can actually change the things that you need changed for your purposes, that you actually now take control over your own hardware, and you actually get the board you actually wanted at the beginning of all of this instead of the board you had to settle for. So, there's some amazing things here. And of course, the first thing you do when the boards don't blow up is you pop open a serial console, you type in all of that, and the bunny comes to life in the most stupid and silly way, because now all I've done is made a really blinky LED. And I've already told you the why, because it actually gives you control. It gives you a better understanding of what the hardware is that you're doing underneath. And frankly, the minute you actually understand how to build hardware, it opens up your what you can do in computers. You're no longer limited by pulling a device off the shelf and using only that. It actually gives you the power and the ability to go and do your own things. And if I can do it, you can do it, although start simple. Don't jump straight to the bunnies. The bunnies are actually kind of hard. And in fact, the bunnies are broken all over the place. So you notice there's 2 buttons here? Turns out documentation is hard. So that talk on, you all listen to that talk on documentation. Listen to them. Because it turns out GPIO 16 on the ESP8266 is unusable, despite it being called a GPIO. It has no pull-up. It has no hardware interrupt. And on this board, it's wired to ground, which means it doesn't do anything. Oops. And at some point, these are actually called battle bunnies because, the bunnies, you're supposed to put them up to each other, and they send random numbers at each other, and whoever has a higher random number generator wins. Except that I have made not an IR receiver, but the world's best random number generator. I don't know why, but all the data that I read off the IR sensor is garbage. Seriously, if you ever want to see it, I will run the program. It is just utter garbage. And I can't figure out why yet. And yet, here I am. I'm tickled pink that, these LEDs up at the top work because that's chained off of a secondary chip because the ESP8266 doesn't have enough GPIOs. So, yay, it works. But, if you do your own hardware, things will break. Be aware of that. You can cry a little bit when it breaks because, seriously, you just spent 6 weeks waiting to get it back and it's broken and, okay. But, at this point, I've spent 40 minutes babbling at you. I'm hoping you have some questions, or at least some comments, or at least to make fun of me. I mean, come on, seriously. I'm used to talks where people literally throw things at me. And you have all been much too polite and much too nice to throw anything at me. So, I will answer anything. My talk, questions, comments, concerns. There's one in the back! Well, midway, I guess, not quite in the back. am I telling you that the documentary Shenzhen I/O? Oh, the game Shenzhen I/O. I'm not actually familiar with that game show, so probably it's all fake.
Oh, it's a video game where you make these. It's
Wait. So there's a video game where you make like the flaming octopus,
No.
or like PCB?
No, you make blinking LED boards.
This is a game?
Yeah. It's called Shenzhen I/O.
You mean I could have been playing a game instead of spending thousands of dollars and hundreds of hours building things over the last many years?
In theory.
And this is where I realize I've wasted my life. Okay. Question. I mean, come on. Somebody else has to have a question. I got to make some more jokes here somewhere. Come on.
Sir, how you insert the code in the PCB?
Okay, so the physical, how does like this chip end up on this PCB? So there's a large machine. Everyone's roughly familiar with a CNC machine where there's a computer-controlled head that goes in the X and Y axis and has a Z axis up and down. So there's basically a giant CNC machine, or a CNC-like machine, where it will go over, picks up a piece out of a feeder mechanism. And there's several different ways that this can happen. And it uses suction to pull this up. Usually on a good machine that will do this, it actually runs it over a camera to double check the placement and to make sure it picked up the right part, because sometimes they pick up the wrong part, or they drop the part, or things explode. And then it moves it over to where on your original layout file, there's an entire orientation and absolute positioning file that you end up generating from that for the manufacturing process. It then places it on little daubs of solder paste. And once everything's on the board, or on one specific side of the board, I should say, they run it through an oven and bake the whole thing in a very specific way, which sets the solder and locks it into place. So that's, and in this case, the ESP8266 actually comes as a pre-done module that looks exactly like that. And you can order them from any number of places.
Sir, if you write a code at one time, can we overwrite the code?
Yes. So in fact, the gentleman, who is the gentleman who was playing with this last night at the hackerspace here? So he's in the back. This is not running the code you were playing last night, is it? I mean, no. So yeah, he's nodding his head that it's not running the same code. In fact, I've overwritten the code on this about 4 or 5 times, and. Oh yeah, no. Apparently, my wife wants me to point out the USB port. It's in the butt, specifically in the tail, which has apparently become a tradition on where all USB ports on boards or devices that I build go. Because so that robot that I showed you that I built, I actually did that several years ago. A second generation of one of those, which is much smaller, there's a USB port where the tail on the dog would go. So yeah, I apparently have a problem with USB ports and butts.
Thanks, John, for a nice talk.
Yep.
It was lightning. So my question is, as you are touching up hardware part, so would you recommend people to use Raspberry Pi just to start with?
So Raspberry Pi is a fantastic board for the simple fact it's $35 for the big version and like $5 for the Zero or something. These are amazing prices. They're not the only boards that you should keep in mind if you're looking for a cheap, full computer, or like full stack computer to work with. At the cheap end, which is where a lot of people like to go, because what's the first thing you're going to do? You're going to let the magic smoke out, and then feel bad because you just let the magic smoke out of a board. And if you do this on an expensive board, like that $40,000 big board, you feel really, really bad. When you do it on a $5 board, whatever, throw it away. So there's the Raspberry Pi. There's the Onion 2. And I'm going to forget which company makes that. It's about a $5 to $9 board. They just completed their Kickstarter, and they're finishing up their Kickstarter shipping right now. There's There's something else running around right now. There's a bunch of stuff in that same range. If you're going to go down the full stack Linux route, try and find something that everybody else is using, because your support for the board will be better. Raspberry Pi is an excellent example because everybody and their dog has a Raspberry Pi and everybody's supporting it. So, and I say that having come from effectively helping build a board that's in the same rough, very hand-wavy category as the Raspberry Pi, but the board I was building, since it was an x86, cost $140 as opposed to $35. But you get an x86 versus an ARM, and then you get into all the, I mean, it's going to, there's a great many things that are going to matter based on what you want to do with it. But just think about what you actually want to do and go for the board that makes the most sense. And yes, the Raspberry Pi is a very good board for a full stack board, not an embedded board. So.
Actually, companies are trying to get rid of the hardware. They are moving for the software-defined radios. They are trying to go for signal analysis through software.
Mm-hmm.
So, how extend MicroPython does it support? I mean, does it support for signal analysis and stuff?
So I am not familiar with anything doing signal analysis on a MicroPython board, but Python's actually got a lot of really good just signal processing type libraries available to it already. I don't know what's been ported to MicroPython. MicroPython is not exactly Python. They've done a lot of things to get Python to actually run on these boards. I mean, this has 4 megabytes of flash, and I don't even remember what, how much RAM it's got off the top of my head, but the microbit's even smaller. So depending on what type of signal analysis you care about, you may not be able to do it on the board, because there may just literally not be enough RAM to process it cleanly. But with things like the ESP8266, you can actually, since you've got Wi-Fi on board and it works under with MicroPython, you can just shove the signal straight off. So you can do all your data acquisition here, and then over the Wi-Fi signal or Bluetooth or however you want to do it, you could shove it back to a bigger machine that could actually do the signal processing. So you could, mostly from an embedded perspective, think about these like in the grand IoT world. These are your like far-flung edge sensor, kind of nodes, not the, I'm actually going to do some, real processing. Although Python generally gives you the option possibly to do some real processing.
Hello.
Hello. Okay.
So I was actually working with ESP8266
Yep.
In last month, but what I wanted to do a threading using MicroPython.
Yep.
But I stuck there. So then I ported the project to Raspberry Pi again. So I want you to comment on threading in MicroPython.
So training in MicroPython, it depends on what you want to do your training on. I mean, it's, if you're trying to talk about embedded development, I would argue MicroPython is amazing, for particularly if you're trying to train people who are already familiar with Python and who are used to working on bigger machines. If you're talking about, trying to use MicroPython as just a normal system, I mean, come on, it's an embedded platform. It's only 160 megahertz, and that's that's crazy fast for an embedded platform. So it's going to, my answer on that is going to be more specific, unfortunately. So.
No, I'm saying
I'm sorry?
Threading.
Trading?
Threading.
Oh, threading. I'm sorry. I completely apologize on that. MicroPython does some threading behind the scenes, but fundamentally, almost all embedded controllers are really intended for single loop operation. They don't have a real operating system, and frankly, you don't want them to have a real operating system, because then they lose all of their interesting appeal in being able to do things quickly, and without a lot of abstraction layers between you and the actual hardware. So. Do I think that we're going to get to the point where embedded controllers have, crazy number of cores, like we've got, CPUs that have 12 cores and a million something or others and gigaflops and teraflops and all that kind of stuff? Yeah. But hopefully they're a little ways out, because it's really nice to only have one CPU sometimes. So, and
yeah, you mentioned as a joke of porting Django to MicroPython. What could be the challenges of doing that?
Oh man, there are so many, it's hard to even begin. The first is that depending on how big your framework is, or Django, I don't know exactly how big Django is off the top of my head, because the last time I used it was, that I've actually programmed against it was quite a long while ago. And again, I'm not a Python person, I'm a Perl guy. So just straight up, how big the library is.
Even if it was like something very lightweight as web.py or something like that.
I mean, it's all going to come down to the same thing, which really boils down to you're limited on how much storage space you have. So I mean, this has the chip that's on here has 4 megabytes, which is huge in the embedded world, like astronomically huge. I mean, we were talking about one particular platform that had 64K of storage on it. Now, you're not going to run MicroPython on that one, obviously. But so that's going to be your first hurdle is, can you even just save the files to the device? The second is that you're RAM limited by quite a bit. I mean, you're talking, kilobytes of RAM, not megabytes. If you're into the megabyte range, you're on a pretty expensive microcontroller. And so what you're going to see in porting code from a big Raspberry Pi style system to something like the Bunny here is just every ounce of RAM matters, every ounce of storage space matters, and this only runs at 160 megahertz, and you can trade a lot of space for CPU time, for whatever reason. You compress things, you uncompress things, or you just you make various trade-offs. But even at 160 megahertz, that's not very fast, and in comparison to the gigahertz that even a modern Raspberry Pi runs at. So,
sir, excuse me, sir.
Yeah, there you are.
Yeah, sir, I am stuck between the choice for Raspberry Pi or Beaglebone Black. What do you recommend for home automation purpose?
That's going to get complicated on what you actually care about doing with it. Knee-jerk reaction, go with the Pi, just because you're going to have a better software support story, in the greater sense. And that's not belittling the Raspberry Pi, or not the Raspberry Pi, but the Beaglebone, because I think the Beaglebone's got a really great community behind it. But the Raspberry Pi's community is just, it's exponentially larger than Beagle's. Now that being said, it's all going to depend on what you care about doing with that board itself. If it's just a gateway device, of the two, it's not going to matter. If you're actually hooking sensors up, the Beagle has more GPIO capability, so if you're going to be hooking up a lot of sensors, the Beagle's going to make more sense if you're going to, versus the Pi. Go ahead.
I am using sensors, lot of sensors. There will be temperature sensors, photoelectric sensors. So it's about complete automation of my home.
If you're backhauling all of your sensors to your Raspberry Pi or your Beagle or whatever, I would lean towards the Pi just from a software perspective. But if you're using a lot of I/O, or if you need a lot of I/O, go with the Beagle. I mean, that's the best answer I can give you.
Thank you, sir.
Yep.
Actually in embedded we write a code.
Yep.
And we compile it and we'll dump the Xcode to the ROM into the embedded chip. And how will be done in here in the MicroPython, and whether it completely puts like a string wise or like after compilation will be flashed into the RAM.
And let me make sure that I've got your question right, because I've already screwed up on one question, it seems. The traditional way is that you compile your code and you flash it in and it's done. And your question is, how does this model sort of roughly work in the MicroPython world? Okay. The way this works in the MicroPython world is that there's actually a file system layer that MicroPython fakes for you. So everybody's used to, open file, write to file, those kinds of things. So that's actually, those commands in MicroPython all still exist. So it's taking that entire flash ROM that you're used to using, and it's actually faked a file system in its own magical brain. And what you can do is, like if you want to save a permanent program that will always run, like, on the Bunny here, I just flipped the on switch and it started doing its thing. There's a couple of files that MicroPython specifically, declares as, I will run this one first on startup, and then I will run this one second on startup. And if you have your code in there to start whatever you want to do, they'll just run. And then when you want to go to production, you just back up the entire ROM out of one, and then just blast it down the exact same way you would blast at any firmware down. I mean, that's how you have to get MicroPython onto a lot of these boards to begin with, is, step one, plug in USB cable, flash MicroPython, and get to that state. So you can always pull the ROM back out and do exactly what you're used to doing from a compile stage. It's just from a quick prototyping perspective, MicroPython means that you're typing commands within a couple of minutes instead of the traditional cycle until you finally get everything working, and then you're like, okay, never touch this again. It works. So.
Sir.
Yep.
So my question to you was, I wanted your opinion regarding the quote that was there by Alan Kay. People who are focused on software should create their own hardware.
I'm familiar roughly with the quote, and I would agree with it. I mean, I would agree with it in its spirit anyway. I'm getting told I'm out of time. So I'll quickly finish this. The real reason is if you're building your own hardware, you actually understand it. And that's, this goes back to my statement on, I've known people who have gotten masters and PhDs in computers, and they have no idea how the hardware actually works. And that, I think, is a fundamental travesty. And so if you at least understand how your hardware works, your code will work better, because you actually understand the interaction. So.
Thank you, sir.
Yep. Okay, thank you very much.
Okay, so